Hello everyone. Today I'm going to present an overview of our proposed system which can efficiently find projected nearest neighbors for LSH techniques. I am Omid Jafari and along with my co-authors, this work was done at New Mexico State University. LSH and its variants are very popular approximate similarity search techniques for high dimensional spaces. In existing disk-based LSH techniques, we observed that accessing the hash bucket index files from the disk in order to find which points collide with the query was the most dominant query processing cost. In this paper, our goal is to improve the performance of existing state-of-the-art locality-sensitive hashing methods by specifically reducing random index IOs. When the desired number of nearest neighbor points are not found in the query hash bucket, state-of-the-art techniques such as C2LSH, QLSH, ILSH use a bucket expansion strategy called virtual rehashing. Virtual rehashing starts from a very small search radius and exponentially increases the radius multiple times until the desired number of nearest neighbors are found. As you can see in this slide, with every expansion of the radius, several random IOs are required for just the few expansions. For the first radius, only one disk seek is required in order to retrieve the contents of the single bucket. But as the radius expands exponentially, more disk seeks are required. We observed that for some datasets, the radius can reach up to 8,000 in order to find top 100 nearest neighbors, which results in significant amount of random IOs. It is well known that random IOs are often a bottleneck in query processing and more expensive than sequential IOs. And we show this for only one hash projection. In LSH, as the dataset size grows, the number of hash projections increase, often ranging in hundreds of projections. Hence, our goal in this paper is to improve existing LSH techniques by reducing the number of required random IOs in disk-based LSH methods. A state-of-the-art LSH techniques use virtual rehashing, which starts processing from radius 1 and then exponentially increases the radius if desired number of nearest neighbor points are not found. The radius is increased until the terminating conditions of the method are met. Virtual rehashing was first proposed in C2LSH and later used by QLSH. For larger radiuses, especially this strategy can lead to excessive random IOs and also overall wasted IOs. In the first figure, the query will expand 3 times to radius 9 for finding the top 3 neighbors, leading to excessive random and overall IOs. This is especially significant when the radiuses are large. On the other hand, ILSH uses an incremental expansion strategy instead of exponential expansion. This way, it reduces the overall IO mainly by reducing sequential disk IOs. However, this reduction comes with the cost of an increase in the algorithm processing time. In our experiments, we show that this bookkeeping has a significant amount of overhead, resulting in overall slower query processing time. In this paper, we present a radius-optimized locality-sensitive hashing technique called roLSH that reduces random IOs and overall IOs without adding any significant overhead to the query processing time. The goal of roLSH is to efficiently find top k approximate nearest neighbors in high-dimensional spaces. We propose a sampling-based technique named roLSH-samp that reduces random disk IOs and thus reduces the overall query processing time. We further improve on roLSH-samp by proposing a neural network-based technique named roLSH-NN to predict projected radiuses and further reduce random IOs for efficient query processing. Both of these techniques are designed by taking two key observations into consideration, which will be described next. We observed that for high-dimensional datasets, the required radius values for a k-value are similar to each other for different query points for a given dataset. The charts in this slide show that for 1000 randomly chosen query points, the final radius values for most of the queries are the same. For example, in the audio dataset, 750 queries out of 1000 are having a final radius value of 8192. Or in the other dataset, which is the color dataset, 755 queries out of 1000 are having a final radius of 2048. Moreover, we observed that choosing an initial radius value that is close to the final radius value will result in less radius expansions and less I/O and processing costs. For example, for a query with the final radius of 6000, current methods start with a radius of 1 and expand until radius becomes greater than or equal to the final radius. However, starting from a closer value such as 4096 will result in less radius expansions. We will first explain our first strategy, roLSH-samp, which is based on observation 1. The goal of this strategy is to find a good starting radius instead of choosing one that existing strategies use to begin. The grade modules in this figure are existing LSH modules that we do not change. In order to find a good starting radius, we leverage our observation that we explained earlier and sample random queries. We choose random queries in the indexing phase, run LSH for those random queries for a given k, and count the number of occurrences of the final radius values. For this step, we use 1000 queries as the sampling size. Thus, the initial radius in the improved virtual rehashing module will be set based on the value found from sampled queries, which is explained in detail in the next slide. Note that this process is in the indexing phase and has no effect on the query processing time. First, the sampling will output different radius values which show the unique radius values for the sampled queries. As a result, a histogram of final radius values will be formed. Since the radius expansions in C2LSH are performed exponentially, a final radius value for a query does not necessarily mean that C2LSH has found all its candidates at that radius, and the candidates might have been found earlier, but excessive data are read due to the radius expansion strategy of C2LSH. The optimal radius can be before the final radius, for example, between 4096 and 8192. As a result, we use the value before the maximum frequency as our chosen radius. For instance, if most of the sampled queries are having a final radius of 8192, we choose 4096 as our initial radius. Further, to reach the optimal radius from the initial radius, we use an improved virtual rehashing strategy, which exponentially increases the radius with increments of powers of c. We explain this improved virtual rehashing strategy in the next slide. The virtual rehashing strategy in C2LSH and QLSH, called OVR in here, exponentially increases the radius while starting from a radius of 1. This strategy is not efficient in cases where the final radius is very close to one of the radiuses. For example, a query in real dataset required a radius of 6000 to return its results. OVR expanded till radius 8192 before it found enough nearest neighbor points, and hence it resulted in wasted random IOs and overall IOs and a slower query performance. In roLSH-samp, we start from an improved radius that is closer to the final radius. This improved radius is found in the indexing phase. However, based on our assumption that the initial radius estimated by the sampling strategy is very close to the actual radius, we perform smaller expansions between the initial radius and initial radius multiplied by c, which is 2 in this case. After that, the same exponential expansions of OVR will be used. Using this strategy, we can stop earlier than 8192, as in this example. roLSH-samp can effectively reduce random IOs, especially when the radiuses are large. Moreover, roLSH-samp can use a small sampling size in order to output a good estimation of radiuses. While roLSH-samp shows improvement over existing state-of-the-art techniques, as we will show in the experiments, we also noticed the two main drawbacks in roLSH-samp. First, roLSH-samp is effective only when the required radius values for a given k are similar to each other for different query points. In other words, all sampled queries should require a similar radius value. We observed that this is not always the case, and roLSH-samp efficiency degraded in those cases. The second drawback is that the radius values change for different k values, and it is not possible to use only one set of sampling results to determine radius for all given k values. In other words, it is not trivial to build a single model and extend it to multiple k values to find the radius for a particular k value. Instead, different models need to be built for each k value, which results in extra time and space overheads. Which leads us to our second important observation. We observed that queries closer in the original space have similar final radiuses for a given k. Since LSH hash functions are generated such that they preserve the distances between queries, nearby queries will also have similar hash values. Therefore, the radius for queries can be predicted by using their hash value in each projection. We will now present our next strategy that uses a neural network to predict the radius based on the hash values of a given query. To overcome the drawbacks of roLSH-samp, we propose a neural network-based strategy called roLSH-NN. roLSH-NN predicts the radiuses based on the given query's hash values in each projection for any given k value. To train our neural network model, we chose random queries from the dataset and used the hash values of the queries in the projections and also a k value as the input to the network. We also input the actual radius, which was found by running query processing on those random queries, as the target value to the network. After several iterations, the network learns to predict a radius very close to the actual radius. Since our problem was a regression problem, we tried several machine learning techniques to find the best one for our purpose. As you can see in the table, multi-layer perceptron gave us the best MSE and R2 for a sample dataset, and therefore we chose it for the roLSH-NN architecture. In the query processing phase of roLSH-NN, the given query is inputted to the neural network model that was trained in the offline phase, and neural network will output the predicted radius. Two cases will happen according to the predicted radius value. In case of overestimation, extra I/O and processing will be performed by the algorithm. However, we experimentally show that our method will still beat the other state-of-the-art methods because it doesn't overestimate the radius too much. In the case of underestimation, radius expansion module can follow the same expansion pattern of roLSH-samp and exponentially increase the radius, which we call here roLSH-NN IVR. However, this strategy might still not be efficient enough when the predicted radius is very close to the actual radius. Therefore, we adopt another strategy where we increase the radius linearly by utilizing a parameter called lambda. We call this strategy roLSH-NN lambda, and next we will show that this design beats other state-of-the-art methods in the overall query processing time. In this slide, we explain the setup of our experiments. In order to evaluate the effectiveness of our proposed method, roLSH and its three variations, we compared them with the state-of-the-art LSH algorithms C2LSH and ILSH. We used three commonly used high-dimensional real datasets in our experiments. Moreover, we tried three different training sizes for roLSH-NN to study the effect of changing the training size. Training size of 2000 queries gave us the best MSE and training time trade-off, and thus was chosen as our default setting. For each query in the training, we use different values of k that are present in the training. We use three different settings to show the effect of introducing new k values in the training phase. We saw a significant improvement in MSE by going from the first setting to the second setting. However, the MSE improvement by going from the second setting to the third setting was small. Therefore, we chose the second setting as our default. Our goal by proposing roLSH was to improve performance without sacrificing accuracy. Therefore, we used several criteria to evaluate each method. Number of these 6, that is the random IOs, and also the total amount of data read. Algorithm time is the time it takes to find the nearest neighbor points minus the IO cost. Query processing time is the total time it takes for the method to return top k results. Finally, we use the same ratio definition as C2LSH and ILSH, which shows the accuracy of the returned results. The closer the ratio is to 1, the higher is the accuracy. In this presentation, we only show the results for the criteria in bold and refer the viewers to check the paper for the complete results. This slide and the next slide show the results of our experiments for the deep dataset. The chart on the left shows the number of these 6 for different k values. roLSH-NN lambda significantly performs the best because it can accurately predict the radius for different k values. Also, as expected, roLSH-NN IVR and roLSH-samp produce more D6 due to radius underestimation, which is because of more radius expansions. It is also worth mentioning that the prediction of radius by roLSH-NN for smaller values of k was not accurate, which resulted in more radius expansions and more D6. The reason for this behavior is that for smaller k values, there are more radius variations compared to other larger k values. And since we have a smaller number of k values in the training phase, the neural network is not accurate at estimating those radius values. However, as it can be seen in the chart, roLSH-NN is still having a smaller number of 6 compared to the other methods. The chart on the right shows the time needed by the algorithms to find the candidates, excluding the time taken to read the index files. The chart is log scale since algorithm time for ILSH was orders of magnitude more than other techniques. This is because ILSH expands the radius incrementally in each projection, which creates a significant overhead. This chart also shows that the overhead of all roLSH variations are very low and the overall algorithm time is close to C2LSH. The left chart on this slide shows the overall time required to solve a given query. All roLSH variations are always faster than C2LSH and ILSH, with roLSH-NN lambda being the fastest because of their ability to accurately predict radiuses with a very small overhead, resulting in significantly less D6 and less amount of data read. The chart on the right shows the accuracy of all techniques. All roLSH variations have close accuracies to C2LSH and ILSH. However, ILSH has a slightly worse accuracy, but this accuracy changes according to the dataset. As for some datasets in the paper, ILSH accuracy is slightly better than C2LSH and roLSH. Our processing times are, however, always faster than the other methods for larger datasets. In conclusion, we saw that state-of-the-art LSH techniques suffer from either excessive disk IOs or significantly slow query processing time. To alleviate these problems, we presented a novel structure called radius-optimized locality-sensitive hashing (roLSH) with the goal of improving random disk with a negligible overhead. In roLSH, we use sampling and neural network-based techniques to overcome the challenges of having the best estimation for projected radius. Finally, we presented experimental results on real datasets to show the efficiency of roLSH as compared with state-of-the-art approaches. Thank you for attending our presentation. We hope you'll find the information useful, and in case you wanted to contact us, this is our contact information. Thank you for your time.